From the University of Arizona Distance Learning Program, this is Optical Sciences 505, Diffraction and Interferometry, with Dr. James Wyant. This broadcast is authorized by the Arizona Board of Regents on behalf of the University of Arizona. Any reproduction or retransmission of this course or use of same for granting of credit without the express written consent of the University of Arizona is strictly prohibited.
Well, I'll say good morning to everyone. See, what's the date today? See, it's Tuesday. No one knows. April 7th, okay? And see, so Thursday would be April 9th. So what happens on Thursday? Anyone have any idea? Holy Thursday, I see. That'd be a good day to have an exam, right? Okay. Well, I forgot to mention that last class, but it's been in the schedule since the first of the semester. There's a class, there's an exam on April 9th covering sections 8 through 13. And so if we go back and look at 8 through 13, 8 is multi-layer films, 9 is phase shifting interferometry, 10 and 11 diffraction, 12 is more on Fresnel and Fraunhofer diffraction, and then 13 is on Fresnel diffraction. So on Thursday then the test will cover those sections 8 through 13. And I'm handing out today a copy of the test that I gave last year and for you to look at. So any questions on the exam? Everyone's ready for it? Okay. So it'll be an hour and 15-minute exam, closed book, closed notes, open mind, and shouldn't be too difficult. The worst part about the exam is grading it, and of course you don't care so much about that. So. Oh. It doesn't have to be difficult. You know, the way to make it easy to grade is to make it so difficult that no one can answer anything, and then it grades rapidly. There's another way of making it easy to grade, too, but I forget what that is. Okay. So last class we were talking about multiple slits, binary diffraction gratings, section 14.5. So I think what we had last class was that we had n slits here. Each slit had a width of b, and the spacing between the slits was h. And we said that we could then just write down the integral over the aperture, e to the minus iky sine theta dy, Fraunhofer diffraction here. And so for the first slit, the way we picked our coordinate system, the lower portion of the slit was at y is equal to 0. So first integral would go from 0 to b. Second one would be h to h plus b, and then 2h to 2h plus b, and so on, up to n minus 1h to n minus 1h plus b. And I think we started to do that integral. And we said the first one is e to the minus ikb sine theta minus 1. And then the second one here, let's write it down. We'll write it down here. E to the minus I k b plus h sine theta minus e to the minus I k h sine theta. And I'll write one more down, I guess. And e to the minus I k b plus 2h in this case, sine theta, minus e to the minus ik 2h sine theta, and so on. We could write all these out. And we can factor out some terms, common terms in all of these expressions. And we get then at this integral over the aperture. Upstairs we could factor out an e to to the minus I k b sine theta minus 1, so factoring that out. And downstairs we have a minus I k sine theta. And so in here we'd have a 1 plus e to minus I k h sine theta. And so on out to finally the last one would be e minus I k n minus 1 h sine theta. Okay. So we look at this, and the first guy we could factor out an e to the minus I k b over 2 sine theta. And so we get an e to the minus I k b over 2 sine theta. And then if we, just like we did last class, we have this beta. It is 1/2 k b sine theta. So we could make this sine beta then. What we have upstairs here is sine beta. And downstairs we'd have a beta, but we have to put a b here then. So b, e to the minus I k b over 2 sine theta, sine beta over beta. And then this guy, this is just a geometrical series. So remember, when we sum that up, we get 1 minus whatever the next term is, divided by 1 minus whatever the ratio is between consecutive terms. So that would be 1 minus e to minus I k n, next term, nh sine theta. And downstairs then it'd be 1 minus e to the minus I k h sine theta. Okay. And now to go to the next step, we're going to make another definition here. We're going to define a thing called gamma, which is going to be 1/2, similar to this beta, but it's 1/2 k h sine theta. And then if that's true, then we could rewrite this. Well, we have a b out in front. This is just e to the minus beta. E to the minus I beta, I should say. And then we have, well, I'll write it down and we'll see if it doesn't make sense here. I'm going to again factor out an e to the minus I k n h over 2 sine theta. So this becomes e to minus I n minus 1 gamma. And we'll see in a second just why it comes out that way. This is a sine beta over beta. And then this one will be a sine of n gamma over sine of gamma. So we factored out upstairs an e to the minus I k n h over 2 sine theta. And downstairs we factored out an e to the minus I k h over 2 sine theta. So that's why we got e to the minus I n minus 1 gamma here. And these phase terms probably not going to be interested in it anyway, because we're going to write down the irradiance here. And we'll just say, well, that's I naught times sine beta over beta squared sine n gamma over sine of gamma squared. But then we would like to have this normalized, so when theta goes to 0, this becomes 1, which it is. And we want the second term here, the sine of n gamma over sine of gamma, to become 1. And so we have to divide here by n. And so that n goes into the I naught. So now when theta goes to 0, I is equal to I naught. So maybe I'll write that down. Insert n to normalize to I naught when theta goes to 0, or we say when gamma goes to 0. Okay, so this is the resulting irradiance. And we look at this, we think here for a second, the sine beta over beta squared, where did that come from? That's just the diffraction due to a slit, okay? And the sine of n gamma over n sine of gamma squared, that's due to the interference of the light from the n slits. Now when we had two slits interfering, we got this sine beta over beta term, and this became a cosine, just interference of two slits. And now we add in more slits, the interference pattern becomes sharper. And we'll see some pictures of it, drawings of it in a minute. But instead of being sinusoidal because of multiple beam interference, the interference fringes are going to be sharper than just sine waves. So you understand physically where these two terms come from. And as n becomes larger, and we'll see this in some drawings in a minute, but as n becomes larger, this is going to become, the fringes will be sharper and sharper. Okay. Well, before we look at the drawings of the fringes, let's look at where the fringes are located. And we're going to have what we're going to call principal maxima, and we're going to have secondary maxima. So let's first look at the principal maxima. And the principal maxima here will occur when gamma is equal to m pi. Because when gamma is some integer number of pi's, this is going to turn out to be a 1 here. Okay, so m is 0, 1, 2, and I could also put plus or minus, I guess. So on. And this will turn out to be 1. And so we're saying here that m pi is gamma. So gamma is 1/2 kh sine theta. So it's pi over lambda h sine theta. And so h sine theta is m lambda, or sine theta is m lambda over h. And m is called the diffraction order. Okay. So I'll draw a box around this. And this is the basic grading equation, at least for normal incidence, that the sine theta is an order number times the wavelength divided by the spacing of the slits. I'll celebrate that result by having a sip of cold tea. Well, I said these are the principal maxima, and if we go back and bring down this equation again, what we're going to do here is play around and find some what we'll call secondary maximas. And these secondary maximas occur in the following condition. Gamma is 3 pi over 2n, 5 pi over 2n, so on out to 2m plus 1 pi over 2n. And there are n minus 2 of these. So if we have n slits, there are n minus 2 of these secondary maximas. And so this is, if we look back here, these secondary maximas occur when the sign of n gamma is 1. But they're not principal maximas because what we have downstairs is something that's going to reduce the size of this. So the whole quantity is not 1, just the numerator is equal to 1. So n minus 1 of these. So when we had 2 slits, we didn't have these secondary maximas. But when we get to more than 2 slits, then we will have 1 or more secondary maximas. And we'll see, again, when we look at some pictures of these in a minute, we'll see these guys. The next thing we want to mention here are the zeros. And the zeros are going to occur when the sign of n gamma is equal to 0. Well, the zeros are going to occur when the sign of n gamma is equal to 0, but the sign of gamma is not equal to 0. And so that will occur at pi over n, number of slits, 2 pi over n, and so on. Then the last thing here we should mention before we look at some pictures is that we have this slit diffraction pattern here out in front, the sine beta over beta squared. And often the slits are small enough that sine squared over beta squared is approximately equal to 1. And so the first few, anyway, principal maximas will have approximately the same intensity. So let's write that down here, that if slits are very narrow, then sine of beta over beta, well, even square it, is approximately equal to 1. And the first few maxima first few principal maxima, let's say, have approximately the same intensity. And if the slits are wide, then this is going to cause the principal maximas to reduce in intensity. And I think we'll see some results of that in a minute here. Okay, well, let's look at some plots of these basically this function here for different values of n. So I'll go back. I gave you a handout, I think it was last class, maybe class before last, I forget now, but on the Fraunhofer diffraction pattern of multiple slits. So I'll get it out here. And the first case, so if we could zoom in on this drawing here, that's good. So the first case we already looked at, that was where n was equal to 2 slits here. And so we got these nice sinusoidal fringes, and there's no secondary maximas in here, it's just a nice sinusoid. Now we go to 3 slits, and I've made the slits narrow. In fact, the numbers I picked was that spacing of the slits was 100 wavelengths, and the width of a slit was 4 wavelengths. And so we have all these several principal maximas here, and we can't see the effect of the sinc squared function because the slits are so narrow. And so this would be the principal maximas, order number 0, +1, -1, +2, -2. And then these are the secondary maximas. We have n minus 2 of these. Well, n is 3, so we have only 1. Okay. And we can see that these principal maximas are a little sharper here than what they were up here for 2 slits. Well, let's increase the number of slits. And so we'll now go to 4. So 4 slits becoming sharper, and we get 2 secondary maximas. 5 slits, still a little sharper. Maybe I can put both these in here and you see. A little sharper yet. And 3 secondary maximas. And then I'll go to 10 slits, and should be 8 secondary maximas here. I'll leave it up to you to count them. And these guys are definitely sharper. And if I were to go to more and more slits, these would become sharper and sharper as you increase the number of slits. And then I just, since I love playing with Mathematica so much, I made another plot here. You can't really, the secondary, this is for 4 slits. And it's a little hard. No, it's for 5 slits, actually. 5 slits. I guess if we look closely enough, maybe we can see 3 secondary maximas there. But the secondary maximas are so weak compared to the principal maximas, it's kind of hard to see. And the last plot I have is where I took just 2 slits for simplicity. And for the red, the slits, well, the spacing of the slits were 100 wavelengths. And for the red, the width of each slit was 4 wavelengths. And so the sinc squared function is essentially unity for the region we're looking at here. And then the green dashed line here is for width of 40 wavelengths. And so now you can see that the sinc squared function really is dropping the principal maximas quite a lot. Okay. So that, some examples for the interference of n slits, and the diffraction pattern we get for n slits. Any questions? You're all experts on n slit Fraunhofer diffraction? Well, Fraunhofer diffraction is not covered, well, at least these examples are not covered on the exam, since this is in section 14. But we will have a final exam, so that will give me a chance to ask a few questions on these. Well, we've gone through a little algebra here, looking at these slits. Let's kind of like to look at a little, physical explanation of a grating, diffraction grating, n slits here. So let's write that down. Physical explanation of this thing we call diffraction grating. And so we have these slits. And they have some spacing that we're saying is h here. And let's say we illuminate this normally, okay? Normal illumination. And some of the light goes straight through, okay? And that will be for the, what we're going to call m is equal to 0. And then we have light leaving at some angle here. And I'll show a couple of beams coming up here, maybe one down here. And let's say this is leaving at an angle of theta. And if I look at the light going through 2 adjacent little openings here, and I draw a normal to the beam leaving here, this path difference here is h sine theta. So this angle is theta, so this angle right here is also theta. So that's h sine theta. And if this is equal to an integer number of wavelengths, m lambda, then the light going through this little window and the light going through this window would be in phase. And so this is when we get maximum light. These are the angles at which we get maximum light. And the light that went straight through would be when m is equal to 0. There's no path difference. And so you'd have light coming up at this angle, say when m is equal to 1 or m is equal to 2. And it could be going at the opposite direction here when m is -1 or -2. So you can see physically why these angles give you maximas in the amount of light. Okay. Any questions on that? Well, that was for normal illumination. Let's look at the case where we have non-normal illumination. And so, I'll pick here. So let's bring in light at some angle here. And let's make that angle theta 1. Okay. And we have light leaving at some angle. I don't know what it is. Say, like so. And let's call that angle theta 2. And so we can draw normals here. One normal there. And a normal there. And so now the condition we have to get a maxima out here is that h, the separation of slits, times sine theta 1 plus h sine theta 2 is some integer number of wavelengths. In other words, h times sine theta 1 plus sine theta 2 is m lambda. So that, at non-normal incidence, that would be the expression that would give us the relationship between h and theta 1 and theta 2 and the wavelength to get maximas. Any questions on that? For m is equal to 0, the 0 order would be what? Just light going right straight through here. And if you think for light going right straight through, we had this distance here and this distance here. These would be equal. And we have to take into account the right convention for the sine, so then that would be h sine theta 1 minus h sine theta 2, where theta 1 is equal to theta 2 would be equal to 0, and so the order number is 0. Okay, any questions on that? Well, what we're going to do for the rest of this chapter is to look at different types of gratings, and we're going to compare how much light we have in the different orders for different types of gratings. So before we look at other particular types, let's continue looking at this binary grating that we have here and see how much light we have for that in the different orders so we can compare that with different types of gratings. So what we're going to do here is look carefully at percent of incident light in each order for a large grading. So we're going to let n become very large here. And we've been looking at these so-called binary gratings. And so let's look at that first, and then we'll go to other types of gratings. So this binary grating we have here has some period associated with it. And we said that the spacing of the grading lines was h. So we'll say the period is h here. And what we had in this was some little opening of width b. And what we said was that the amplitude transmission here in the opening is 1, and every place else is 0. So that's why we call it binary grating. Transmission 1 or 0. And so if I go to the side here and think, what is it we have? Well, we have this large grating here of width, I don't know, w. I won't worry too much about that. And we have all these little slits here. Spaced h. And each guy has a width of b. And we have a lot of these. So I'll just let that run off the side of the screen. There's going to be a lot of them there. And if we take the Fourier transform of this, which we've already done when we looked at the Fraunhofer diffraction, that would be equal to, leave a little space here because I'm going to write something there in a second. We had the sine of pi over lambda b sine theta divided by pi over lambda b sine theta. And we had the sine of n pi over lambda h sine theta. And down in the basement here we had an n sine pi over lambda h sine theta. Put a bracket there. And normalize this, we'll put an n and b here. So b being the width of each one, and we have n of them. Now we want to let n become large. Lots of slits. And so remember, as the number of slits increased, the fringes got sharper and sharper. And so this function here, sine of n pi over lambda h sine theta over n pi over lambda h sine theta. As we let n become large, what do you think is going to happen to this thing? We're going to get sharper and sharper, and finally we get a delta function here. If you like, comb function, maybe you want to call it, but I'll write sine of theta minus m lambda over h, and m is 0 plus or minus 1, plus or minus 2. So delta function, comb function here, a bunch of peaks we get here. So we're going to have light only at the locations here where sine theta is m lambda over h. So we can write here, going back to the Fourier transform, normalized Fourier transform. Okay. So this was just our sinc function, and then we had the sine of n something times n sine of that something. And we're going to let n become large. So the normalized Fourier transform here is, I'm going to write that as a Fourier transform of this amplitude transmission function divided by the total available area. Total. I'm just doing this in one dimension, so I'll call it total length. And so that's the Fourier transform, T sub A. And we have n slits, and the spacing of them is h, so it's nh. Okay. I'll give you a chance to catch up on the writing. I'll take an opportunity to drink some coffee. Question?
Just on notation, you have that as capital T of A.
I missed what you said.
It's written as capital T of A, but is that in the...
That's the amplitude transmission. T sub A. You use little t if you want, or capital T, I don't care.
Little T of A is being before the Fourier transform in the previous notes.
Okay. Well, in any case, that's the amplitude transmission. So now we're going to make a little table here of how much light we have in a given order. And so I'll slide that up here, I guess. So we have order number. Normalized Fourier transform, and percent of incident light in order. So first order number, I pick 0. So m is 0. And so we go back here, we will get then that the amount of light in that order is just going to be B over H. I mean, a normalized Fourier transform is just B over H. So that's just going back to taking this, normalizing it, so we're multiplying by n times h, and putting in that the order number m is equal to 0, so sine theta is equal to 0. Yes,
in the denominator for Fourier transform of TA, up on over 1.
Okay.
Is there supposed to be a sign in the denominator? N sign?
Yeah, it's n sign. Remember when we did this, go back a few pages. When we went through and calculated this, you get sine of n gamma divided by n sine gamma. While over here we got the sine of beta divided by beta. So it should be what I've written here. Well, as n becomes large, remember this gets sharper and sharper as the number of fringes increases. That as we move off from the order position, this is going to go to 0 very fast. And so in the limit that we let n become very large, go to infinity, this becomes, I wrote it as a delta function here, or maybe you want to call it a comb function. So this is going to be 0 unless sine theta is m lambda over h. Okay, you're not convinced, maybe.
Well, in the denominator, sine n pi over lambda, you're setting it goes to the delta function, but in the denominator there's no sign there.
Well, sine of pi over lambda h sine theta. Okay.
In the denominator.
Oh, I see. I'm understanding what your problem is now. I guess I was just checking to see if you're awake or not. You were, but I was not. So here's what my problem was. I didn't copy this down right. So that's sine of n pi over lambda h sine theta, and this is supposed to be n sine of the quantity pi over lambda h sine theta. So I just copied this down here. Now do you feel better? Yes. Good, thank you. Okay. So we plugged in the order number was 0, m was equal to 0, so sine theta is equal to 0, and what we get here then is b over h. We normalize, divide by nh, and so the percent of light in that order would just be b over h squared. So it's a ratio of the width of a slit to the spacing of the slits squared. It's what percentage incident light we have in that order. Plus one order. Now, so m is going to be equal to 1. And so sine theta is lambda over h. So this becomes sine of pi b over h divided by pi. And so that, and then percentage of light in the first order then would just be that squared, or sine squared pi b over h divided by pi squared. And if we go out to the mth order, so now sine theta is m lambda over h. Normalized Fourier transform becomes sine of b over h m pi divided by m pi, and this then becomes sine squared of b over h m pi divided by m pi squared. So this gives us how much light we have in a given order as a function of ratio of b over h. And if I want to now calculate, well, I'll slide this up here and calculate, I want to get the maximum amount of light in the first order. So for max light in first order, so we had the amount of light in the first order was sine squared of pi b over h divided by pi squared. B over h should be equal to what to get the maximum amount of light in the first order? 1/2, good. So the ratio of the width of the slit to the spacing of the slits should be 1/2. And the percent of light in first order is equal to, well, we get a sine squared, that becomes a 1. So it's 1 over pi squared. 1 over pi squared. So we have a binary diffraction grating. We make the grating to get the most light in the first order. So that means that the width of the slit, the spacing of the slits is 1/2. So it's what we would say is a 50% duty cycle. Maybe I should write that down. 50% duty cycle. Okay. And so the percent of light in the first order is 1 over pi squared, which is about 10% or something like that. Okay. So this is something that we're going to come back to in a little bit here. We're going to look at some different types of gratings here. And we're going to compare how much light we have in the first order for these different types of gratings compared to this. Now I'm going to go off to the side here just a little bit and do something a little different that I have to throw in here someplace, I feel. And I might as well throw it in here right now. And that's looking at the resolving power of a grating. And then we'll come back and look at all these different types of gratings. So this is actually 14.5.2, and it's something that is kind of interesting. I need to look at it at some point, so let's look at it right now. So if we think here, what am I talking about, resolving power? If I think here for a second, if we take a diffraction grating and we illuminate it with light, the light's going to leave at some angles for different orders. And we had the h sine theta is m lambda for normal incidence. And so the angle that the light leaves depends upon the wavelength. And so when I'm talking about resolving power here of a grating, what I'm talking about is how small of a change in wavelength can I detect? Okay? So how small a change in wavelength can we detect? And you have to, and we're going to define something called resolving power, called capital R, which is going to be defined as a wavelength divided by the smallest change in wavelength I can detect, or delta lambda. And we're going to say, we have to pick some criterion for saying we can resolve different wavelengths. And what we're going to pick here is that the maxima of wavelength lambda plus delta lambda, let's say, falls at minima of wavelength lambda. Okay? So max of wavelength lambda plus delta lambda falls at the minimum of wavelength lambda. Okay? And just to repeat here, we had the I was I naught sine of beta over beta squared, sine of n gamma over n sine of gamma squared, and beta was pi over lambda b sine theta, and gamma was pi over lambda h sine theta. Just repeating what we had here. So now what we want to do, we want to look at this sine of n gamma over n sine of gamma, find a location where we have a maxima, and then see how much theta changes when we go from the maxima to the next minima here. Okay? So what we will say here, to go from the maxima to the next minima here, the change in n gamma is pi, to go from maxima to next minima. Okay, so n gamma will change by pi. So we would have here the angle for that will be when pi is n pi over lambda h cosine theta d theta. So that's a change in theta and going from the maxima to the next minima. And so that's where gamma is changing by pi. And we have here that, so that says that delta theta here is what, lambda over n h cosine theta. So that's a change in angle between maxima and minima. And if we go for order m, we see sine theta is m lambda over h. And so if the wavelength changes, delta theta will be m delta lambda over h cosine theta. So that's a change in angle as we change the wavelength by amount delta lambda here. So theta change for wavelength change of delta lambda. So what we're going to do is to set these two equal here. And so we have lambda over n h cosine theta is m delta lambda over h cosine theta. And lambda over delta lambda then is n times m. Okay? You want me to go back to where? Okay. So what we've done here is that we found the change in angle in going from the maxima to the next minima. And we found that delta theta was lambda over nh cosine theta. And then we said, well, what if we change the wavelength, how does the maxima move around? Well, the maxima will move around by an angle delta theta here, so I just take the derivative of both sides. We get delta theta is m delta lambda over h cosine theta. So that's how theta changes for the wavelengths change. And so we have set these two equal. And we end up with the result that lambda over delta lambda is n times m, and we're defining that as a resolving power, Rp, or maybe just R. And so this is the order number, and this is number of slits. Okay. So this is giving us where the max of one wavelength is at the min of a wavelength plus delta lambda. Okay.
On the previous page, from a delta and gamma to a cosine theta, delta theta, wouldn't that be a sine theta minus sine theta plus?
Wait, where? Okay. How did I go from here to here?
Up further. Where you wrote down cosine theta, delta theta?
Yeah.
Where'd that come from?
Okay. This is the change in theta such that we go from a maxima to a minima. And we have that
Equal to pi?
we want the change in n gamma to be pi. This will go from a maxima to a minima when n gamma changes by pi. Okay, so gamma has a sine theta in it. And so I have n gamma here. It's just this times this. And I want to see how theta changes as this changes by pi. So I take the derivative here, and so n gamma is going to change by pi. And I take the derivative of this with respect to theta, so I get n pi over lambda h, and I get cosine theta d theta from the derivative of sine theta. And so this is equal to pi. And so delta theta is lambda over nh cosine theta. So the ratio of the wavelength to the smallest change in wavelength that I'm detecting goes as n times m. And we're defining that as a resolving power. And this will be when the maxima of one wavelength falls at the minima of the wavelength plus delta lambda. Okay, any questions here? Well, this is kind of an interesting result if we think about it for a second. If we take a grating, and normal incidence, light leaving here at some angle theta, so this is the mth order, the OPD between adjacent open slits here will be m wavelengths. Okay? And we have n slits here. So n times m is simply the OPD in wavelengths across the beam. So n, right here someplace, n times m is optical path difference, OPD, in wavelengths across beam. And so the resolving power we get depends upon the optical path difference in units of wavelengths that we have across the beam. And I think before, when we talked about other types of interferometers for measurement of wavelength, we got a similar result here, that always the resolving power you get is proportional to the path difference you can introduce in units of wavelengths. Okay. Any questions on this? Resolving power over diffraction grating? Well, this was a little bit off the direction that I'm going right now, but I thought it's something that we want to, that we have to talk about. So let's go back in the direction that we were going before, where we're starting to look at different types of gratings, and we're looking at how much light we have in a given order. And we said for a binary grating of 50% duty cycle, we got 1 over pi squared of the instant light in the first order. So let's look at some other gratings here. And the next one is, I don't know, I think I might have my numbers a little bit out of order here. The last section I called 14.5.2, and I think it should have been 14.5.1, but 14.5 point question mark, I guess. Let me go back and change this to a 1 here, 14.5.1, and then I can make that 14.5.2. In any case, the title here is Binary Phase Grating. So what we're going to have here, kind of interesting little beast. We're going to have something here with a period of, for some reason I've switched here from H to D, but I'm going to say a period of D. And we're going to put in here 2 openings. One opening of width B up here, and the other one of opening, should be the same amount here, of B. And opaque every place else. And this guy is going to introduce a phase of, well, we'll write the transmission functions e to the I, 2 pi, m prime over 2, and this is e to the minus I, 2 pi, m prime over 2. So this is our amplitude transmission function. So phase here of 2 pi m prime over 2, phase introduced here of minus 2 pi m prime over 2. And grating spacing of D. And maybe my drawing's not so good, but I'll make this over a quarter of a period here, and this is 3/4 of a period there. So now we have to calculate the amplitude transmission of this guy. 2 pi m prime, I don't know, I use m prime for some reason instead of m, over 2. Well, I know why I used m prime. I don't want to get confused with the order number. So phase 2 pi m prime over 2, phase minus 2 pi m prime over 2. Normalized Fourier transform. going to put B over D here. And then it's going to be similar to what we had before, except inside here we're going to have two of these. We're going to have to add up. And so I know, well, I don't know just what I'm going to get here right now, but I know that one thing I'm going to get is an e to the I, 2 pi, m prime over 2. And for the next guy down here, I'm going to get e to the minus I, 2 pi, m prime over 2. Okay. So one slit this, the other slit this. And I know that I'm going to get a sine of pi over lambda, b sine theta, divided by pi over lambda, b sine theta. So that's our sinc function coming from the width of this slit. I'm going to get a similar thing down here. Sine pi over lambda, b sine theta, pi over lambda, b sine theta. And I'm going to have a lot of these guys, a lot of slits, and so I'm going to get the delta function of, a comb function if you like, but I write it just delta of sine theta minus m lambda over d. Okay. So everyone sees where I guess where I've gotten this, but there's something else I have to put in here, because I don't have one slit, I have two slits. Furthermore, that slit is not in the center of the period, but one is shifted a quarter of a period to the left, and the other one is shifted a quarter of a period to the right. And we could go through the algebra and determine just what this factor is here, but maybe we can go back and, I hate to mention Gaskell's name, but think about something Gaskell taught us, and taught you. He actually taught me something yesterday. I was on an exam with him. I'll see if you know what this is. You know what a PhD camera is? Yeah. Oh boy, this a push here dummy camera. So he must have told that joke in his class? You figured it out by yourself? Oh, whew, I was worried. Maybe it was too much like Gaskell. I was worried for a second here. Yeah, a push here dummy camera. Okay. So right after this class, I'm on another exam with Gaskell. This time it's a final PhD exam for Eric Novak. So see what I learned today from him. Anyway, in his course, he had something about as you shift things around. What's this theorem we have? What, the shift theorem? Okay. And if I shift this a quarter of a period, I don't know if you remember this or not, but you could go through all the algebra and show it, I'm sure. So one of these guys is going to be shifted an amount E. I mean, you're going to get a phase shift that goes, it's E d over 4 k sine theta. And the other one is going to be E to the minus I d over 4 k sine theta. And I'll leave it up to the interested student to go through and prove if that's right. Or probably just think about it, you'll see it's right. So we get a phase shift here, e to the minus, well, the phase shift goes as d over 4 k sine theta, so we get e to the I d over 4 k sine theta, and an e to the minus I d over 4 k sine theta. So this is what we get when we do the Fourier transform of this transmission, of these two gratings, two phase gratings here. And now, if we play with this equation a little bit, what we can write this as, come down here. So if you had heard that before, is it possible that was not an original Gaskell joke?
You told it a long time.
Oh, maybe. Okay. I see. Okay, so anyway, this would be, I'll ask him today if that was original. I'll tell him that you said. that Rob Johnson says it was not an original joke. Okay. We'll see what he says. You could probably transfer someplace else. Okay, we go through, calculate this. We're going to get, well, we have this sinc function in both of these terms, so I can factor that out. Sine pi over lambda b sine theta divided by pi over lambda b sine theta. And we have this thing, delta function sine of theta minus m lambda over d. And then when we multiply this other out here, we get a 2 cosine of 2 pi m prime over 2 plus d over 4 lambda sine theta. Okay. So this is the resulting normalized Fourier transform for this binary phase grading. And we could make a little table here, maybe I have enough time to do it in, of order number and then the percent of incident light in order. So I'll go to a clean sheet of paper. So order number, percent of incident light in order. So order number is 0. Put in m is equal to 0. Go up to this expression here and then square it. We're going to get a b over d squared 4 cosine squared of m prime pi. Okay. And we'll come back to that in a second, or maybe in a week, depending on how much time we have here. Plus 1 order. This becomes a little more complicated when we multiply this out, but we get a 4 sine squared pi b over d divided by pi squared cosine squared of 2 pi m prime over 2 plus a quarter. Okay, so m was equal to 1 here. So sine theta is lambda over d. And we could rewrite this as sine squared of pi m prime. Because we have this last term is just pi over 2, and so that cosine squared becomes a sine squared of pi m prime. Okay. Order number m, this becomes 4 sine squared pi, yeah, let me scratch it out and make that b over d times m pi. So sine squared of b over d times m pi divided by m pi squared, and we get cosine squared of 2 pi m prime over 2 plus m over 4. Okay. Everyone agree with that? So if we look here, some interesting things are going to come up here. The first, if m prime is equal to 1/2. See, this is looking at the 0 order. If m prime is 1/2, so we have cosine squared of pi over 2, so that's 0. So we'll have 0 light in 0 order. And if m prime is equal to 1/2, that means that, go back here, one of these guys is e to the I 2 pi over 4, or e to the I pi over 2. This one is e to the minus I pi over 2. So these two apertures, the light transmitted through these two apertures, is out of phase by 180 degrees. So the two apertures are the same size, and the two apertures are out of phase by 180 degrees. The light going through the two apertures is out of phase by 180 degrees. So we have 0 light in 0 order. That's kind of interesting. Now we want to look at how much light we get in the first order. And without looking at equations, can anyone guess how large B should be compared to D to get the maximum amount of light in the first order? Well, you guessed, but half. Okay. Yeah, maybe. You know, what I would kind of guess here is I would make these half, and I would make the phase difference. What would you guess for the phase difference to get maximum amount of light in the first order?
90.
Well, one would be plus 90 and the other would be minus 90, so it's going to be 180 degrees. And how much do you think we'll get in the first order? For a single aperture in the first order, the maximum amount of light we got was 1 over pi squared. 2 apertures, phase improperly, maximum amount of light in the first order might go as maybe 2 over pi squared. There's 2 apertures, and about out of time, so I better just write down the answer here. If B over D, to get the maximum amount of light in this first order, B over D should be 1/2, and M prime is 1/2, so the two are out of phase by 180 degrees. And if you plug that all in here, you then will get that 2 over pi squared. So 4 over pi squared is percent of light in first order. So by having these two apertures, making them out of phase by 180 degrees with respect to each other, we have picked up 4 times as much light in the first order. Okay. And it's really 2 apertures properly phased, so the amplitude doubles, and so the intensity goes by 4. Okay, well that's about all I have time for today. Next class we'll have the exam over sections, 8 through 13 I said, and then the class after that will go to sinusoidal gratings, amplitude and phase gratings. So I will see you bright and early Thursday morning.